In lecture 14, from here, we are going to cover several organic photochemical reactions, and also going into the metal complex reaction. So let's at first check out what kind of light absorption involved in for organic molecules based on the structure of the bond. So you could see triple bond, it's around 180 or 70 nanometer. And you'll see a CN or C double bond is also somewhere around 200 nanometer. And also, for a conjugated double bond, it's around 200, 230. And if you use benzene, it's around 260 nanometer. And if you connect the carbonyl, it's further into the visible region, visible direction, it's still 300 nanometer, and so on. So what I mentioned is most of the optical absorption and for these organic chemical bonds in the region of UV region. That's why we need a UV light source to induce the photochemical reactions mostly. Let's first study the photochemical reaction of olefin, meaning the double bond. So let's take an example of Stilbene, which is one of the typical trans-cis photoisomerization reaction. You may know that this is trans isomer of Stilbene, and then this is a cis isomer, and this conversion can be induced by light, and also by heating up, it returns back to trans isomer, because the trans isomer has lower energy. So the stable structure is trans isomer. Why is it this happened? As it's just simply you can think about the CC double bond. So as you see, a CC double bond is made of the sigma bond and pi bond, and we've already studied the reason why this is in the plane, the same plane, is due to the pi bond, right? So what I mean is in the ground, the bonding orbital of the CC is something like, so that makes a pi bond, bonding orbital. And two of the electrons are in this region, right? In this. So two electrons are in the bonding orbital, in the ground state. Ground state. And however, excited state one of the electrons is excited to this, so it's getting unstable if they are in the same plane. Right? So what happens here is, if you think about the AB plane and take the reaction coordinate of the A plane, B plane angle, and take the energy. Of course, initially, the ground state angle 0 is better, but if this pi orbital is getting rotated, right? If you are trying to rotate this, the energy is getting higher. So it's something like this. This is S0, so ground state. However, on the other hand, excited state, since you have one electron in this orbital, so it's better to rotate. So the starting from 0, it's actually lower wise angle. That's why when the light is illuminated and to go to the excited state, it's going down to and relax. So at this point, it's for example, it's maybe 90 degree around. So after excitation, try to stabilize this pi bond orbital. It gradually rotates the molecular plane of A and B, and then go to cis, and then at some moment there's some chance to going back to trans or cis isomer. It depends on the probability. So this is the explanation of trans-cis photoisomerization process. Okay. And this kind of the photoisomerization happens even for some of the cyclic olefin. Right? So cyclic olefin means that you have a double bond, but the other carbon is somehow has a cyclic structure, like cyclic hexane in this case. See, so in this case, you could see that cis isomer is actually more stable, because if you make the trans isomer, you could see that the structure is more kind of has a molecule has a strain that has more energy, right? So this kind of strain actually induces some chemical reaction, because since it has more chemically higher energy, and the molecules want to release the energy to make the configuration more stable. Okay. So what happens is, so when the light is illuminated and change to have strain energy, and this molecule has the ability to accept the proton, because this double bond is going to have Lewis base. So in this case, for example, here the double bond has a the ability of Lewis base, so accepting proton, and that makes so carbocation species. So here's one of the example here. By illuminating the light, it has a strain energy, and it's going to accept the proton, right? And so two possible position of the proton can be, and then it's going to give a two type of carbocation, this one, or this one. But due to the stability of carbocation, so stability is this one is good. And then if you have methanol, the methanol can attack the nucleophilic addition. That gives like this. And also if the proton is released, it can generate like this olefin, X olefin to